Hello, everybody. Thanks. First of all, I want to thank DDN for letting me speak in their booth. Appreciate that. I'm going to be talking about how we at NVIDIA partner with DDN to deliver high-performance networked storage to AI applications. So AI data centers are different. Obviously, they have very high-performance compute, but there's more to it than that. I don't see a lot of dads out there, but does anybody have or know teenage boys? Have teenage boys at home? No teenage boys? Well, teenage boys, I'm asking because teenage boys and GPUs have something in common. They're both always hungry. But unlike the boys who are hungry for what's in your refrigerator, GPUs are hungry for data, and lots of it, and they want it fast. So this chart here shows how a CPU typical data set is measured in megabytes, gigabytes, whereas a GPU's data sets are measured in terabytes. And not only terabytes that are slow data, but they want the data super fast. And if we use our analogy of the teenager, the reason is because we all know that CPUs have tens of cores, but GPUs have tens of thousands of cores. So the analogy is, if you're feeding a family, you can do it with the normal kind of storage. But if you're feeding GPUs, you need basically an Army division worth of storage. So let's look at, and also it has to be super fast and super low latency. So let's look at some of those applications. One that's super popular today are large language models. So this chart shows over a 4-year period, starting 5 years ago, how many parameters are needed for a large language model. Sorry, there's feedback if I get too close to that. For a large language model. And you can see that even 4 years ago, it was hundreds of millions, which already seems like a whole lot of parameters. But last year, it was up to 1 trillion. So that's 1 trillion parameters needed to feed a large language model. And that's just one AI application. So this is where the partnership between DDN and NVIDIA comes into play. So there's no way you're going to hold those 1 trillion parameters in local storage. So you need to have remote storage. And DDN makes great remote, high performance, low latency storage. But typical data centers don't have the low latency, high bandwidth networks to get that storage to the GPUs. And that's where NVIDIA networking comes in. We have network adapters, NICs, that can support up to 400 gigabits per second with latencies of right around a microsecond or less for InfiniBand. And those NICs support both Ethernet and InfiniBand. We have switches, both InfiniBand and Ethernet, that can support up to 128 400 gigabit ports. And those can be clustered together into tens of thousands of networks of tens of thousands. And then there's DPUs, which I don't know if you noticed, but DDN made an announcement or put out a blog on how they're using DPUs to accelerate the performance of their storage appliances coming up with some future releases. But it's not only just the wires, the wires that need the high performance, or I should say fibers. It's not just the hardware and the wires. It's also a tightly integrated system from the GPU applications through the network to the storage. From a GPU application perspective, is a technology called GPU Direct Storage, or GDS. From the network perspective, there's software that looks for things happening in the network that shouldn't be, and quickly resolves those with tools like what just happened and automated routing around problems and advanced high-performance congestion control. In the DPUs, there's a software package called Doka, which helps to offload, isolate, and accelerate storage applications. So all of that together needs to be tightly integrated to get the highest performance possible. So looking a little bit deeper into the DPU, so the DPU has an ARM processor that's easy to port your applications onto. It has high performance network ports, PCI ports, accelerators for storage, accelerators for security, all the tools needed to really optimize the performance needed for anywhere up and down the data path for storage moving to AI applications. Looking into the guts of the GPU, or the DPU a little bit more, you can see that the main data path goes from the network ports through the accelerators and the ARM processors and the RISC directly to the PCI ports. That's the main data path. And there's on-ramps and off-ramps for the ARM, for the accelerators, for the RISC-V, and they all of those share a common memory pool of cached SRAM with backed up DDR5 memory. So they're able to support applications, for example, if it's a JBOF for moving data that comes in the network port as NVMe over fabrics, it maybe has data in-flight encryption on it that an encryption accelerator de-encrypts. So now the engine for NVMe over fabrics is able to, the acceleration engine for that can take and de-encapsulate that NVMe over fabrics packet and move the data directly to the SSD, the request directly to the submission queue of the SSD, monitor the completion queue, move the data back, re-embed it into NVMe over fabrics, the answer, and re-encrypt it and send it out without any interaction with the ARM application at all. All of that is done in hardware acceleration to maintain high performance. Other applications that are possible, there's an embedded PCI switch. So other applications that are possible is you can take the storage, interface it to a GPU across the PCI switch using GPU direct storage that I'll talk about in a minute, all without a lot of interaction of the ARM processor. The list is endless of people who are implementing on the DPUs today, storage applications and applications across the board. Doka is the framework. It's an open source framework that's based on Linux that's used as a way to accelerate development of applications on DPUs. Think of it like the Mac OS or Windows is for your laptop. It's based on open source drivers, open source projects like for storage, SPDK, and it really lets you accelerate that development. There's also a rich partner ecosystem. So there's an ecosystem of partners writing software, putting it into the ecosystem. There's almost, I think there's probably around 5,000 now because they're coming like crazy. And it's not only for storage, but that's what we're going to focus on here. So let's look a little bit deeper on the software-defined storage use case. So there's not only software-defined storage that runs on a CPU today, but also other software-defined applications like security and networking and management. And all those take about 30% of a standard server. If you move them to a DPU, in this case software-defined storage, you're saving 30% of that CPU. So you've automatically gotten more cycles on that CPU by moving those applications to the DPU. Also, you now have a fence that protects all those software-defined capabilities from corruption or hacking from the CPU side, because it's only connected across the PCI bus, and I'll show you how that works in more details coming up. So there's no way for applications running on the CPU to get to those functions now. So now you've secured the networking, the storage, the management, and the security by moving it to a DPU, and you've offloaded 30% of that CPU. So those cycles can now be used if your platform as a service, you have a more powerful, if your VMs as a service, you have more VMs, whatever you want to do with that from a customer base. If we go to the other end, if you go to the other end of the storage data path, there's a JBOF or a JBOD, or a standalone, maybe a standalone cold storage server. And you're able to use those same storage accelerations to now use a much lower cost, lower power consumption ARM processor running your software that manages that appliance than a high-end CPU that's designed for as many VMs as they can cram on it, very high-powered, very expensive. So how does that fence work? So basically, what the Bluefield does is use a technology that's marketing term for it is SNAP, and it's actually multiple emulated interfaces that is all the host that the DPU is plugged into sees. So if it's a software-defined storage application, all it sees is all the user of that application that's now running on the DPU sees is either a standard NVMe interface or a standard VirtIO block interface. In the future, we're going to have VirtIO file, but that's probably later next year by now. But in any case, that's the only thing that the user sees. The rest of it is all accessed, or is all stored or running now on the ARM processor of the DPU. So now you can, like if we follow a packet through this, the packet or the request would come from whatever the application is on the host as an NVMe request or a VirtIO block request, crosses the PCI bus as an NVMe command, goes into the Bluefield. The ARM takes a look at it. It maybe has already set up accelerators that are going to handle it automatically, but your software, the software-defined storage stack, can now do whatever it wants with that storage, add its magic. It could convert it to iSCSI, it could convert it to file, or it could use the accelerators to just connect it to NVMe over fabrics automatically across the network, all in hardware accelerators to get very high performance. You could also connect the local storage to that DPU and now isolate all the storage from the users and control it completely by your software storage stack, your software-defined storage stack on the DPU. So now we're going to look at GDS. So GPU Direct Storage is part of a technology or a framework called Magnum IO. Magnum IO is a framework that's designed to accelerate GPU applications. So GDS is part of it, GPU Direct Storage. And what it does is bypass the CPU when it moves storage, like from DDN's storage appliances, in and out of the GPU. So in a regular pre-GDS setup, a request would go out for storage from the GPU, say a read request. It would come into the CPU would put it in its memory, then from its memory it gets moved into the GPU memory. With GDS, the storage request uses RDMA, DMA locally with the local drives, or RDMA for remote storage, like with DDN appliances, to move the data across the network from the memory of the DDN system directly into the GPU memory, saving a lot of cycles on the CPU, but also reducing latency and increasing performance dramatically. So DDN is one of the early implementers of GDS, one of our early partners in that, and they have that in their products for almost 2 years now, I think. They're also part of our partner program. What our partner program does is give them early access to what our roadmaps are, gives them interface to our expertise on GPUs so that they can get our training. It allows them to work with us on white papers for solution briefs and many different things, including a really important one, which is the reference designs. And reference designs are important because it allows us to quickly deploy solutions, AI solutions around not only the networking and the GPUs, but also the storage partner, in this case DDN, to implement quicker, support less, and duplicate very fast across a lot of different customer base.